Hello, good afternoon, everyone. My name is Ajay, as introduced. So I work with IBM, and I've been associated with this quantum safe cryptography for quite some time. I'll be talking about that relevance the for the telecom sector as well as the overall general knowledge about it. All right, so IBM has got a twofold mission for the quantum area. One is the bringing useful quantum computing to the world. And as you can see, our quantum computer replica is right there on this side of the stage. If you are not yet visited, please do visit so that you can understand more about what is a quantum computer, what does it do. But we will be bringing a lot more use cases of quantum computing to the world for the betterment of the world. The other part of our mission is make the world quantum safe. And I will talk about what do you mean by making it quantum safe. Isn't quantum computer supposed to solve great different new things and problems? Yes, it is supposed to solve that, as well as it might be an emerging threat for us all. I'll talk about that part as part of my session here. So what is a quantum computer? Let's begin with that. A little bit more understanding about quantum computing. We are all used to the current binary kind of a computing mechanism, which is zeros and ones. The quantum computer is able to have all the states between 0 and 1 represented at the same time. And that is being done with something called as qubit. It's a totally different type of a computing mechanism of quantum physics as a mechanism that is being used to do all these kind of computations. And the quantum computer replica that you see on the side of the stage, that will really explain or help you understand what does that mean in terms of a quantum computing versus a classical computing is what we have been saying now. So it can solve several kinds of problems that we cannot solve now. It can actually do a lot more things which we do not even aim to solve right now. And there are certain problems that classical computers cannot do and quantum computer can do is something called as prime number factorization. Remember this word, prime number factorization, is important for us for the cryptography part of it, and we will be talking a lot more about this. But this is one of the areas of a mathematical problem. So it's all about mathematical problems to be solved, doing a lot of modeling around sparse data, and then be able to come up with new discoveries and conclusions. So all our current cryptography is based upon a simple mathematical problem called as P into Q. Prime number factorization. If you are given two prime numbers, you can easily multiply and find the product. But if you are given a product, you cannot find the two prime numbers that make that product easily, especially when the number is large. And we have been able to put this problem to the current classical computing computers, and it cannot solve that easily if you keep on increasing the key length. And as you can see, 2048-bit integer is what we have currently got as a key size that is able to give us a protection. Why does it give us a protection? Because this will take a whole lot of time and energy, power, computing resources for us to solve with the current classical computers. On all of this basis, IBM had come up with a standard algorithm for this prime number factorization in 1974. And that has become the world standard for now, and we have been using that for decades. There has not been any threat to that algorithm so far, but going forward, what will happen? And as you can see at the bottom there, the RSA, DSA, the public key encryption, and many such other variants of the same mathematical problem that are currently being utilized world over for us to do the encryption. It will take us millions of years, if not less, to solve with the current computing capability this kind of a problem. But Peter Shor has been another researcher who has proven theoretically that with his different kind of an algorithm, you can actually solve this problem much faster, given you have a different kind of a computing power. And what that computing power is being brought by quantum computing. Remember on the last slide I was talking about some problems that the quantum computer can solve rather easily. That is that prime number factorization problem can be solved by using Peter Shor's algorithm and quantum computing capability. You can solve that the encryption problems in just about an hours. given you have enough number of qubits available. So the quantum computing generally has got number of qubits, error corrected qubits is what we look for. And those number of qubits, they are rapidly increasing. IBM has been at the forefront of the technology innovation along with many other academic partners and industry for the quantum computing. And we believe that in near future, in another few years, we'll have enough computing capability for the quantum computers to break those algorithms, the ones that are currently utilized. But where are they getting used? So it's almost anywhere, right from your mobile device and mobile applications and browser back up to the financial systems, all the back-end operations that we do for the financial systems, the critical infrastructure, which includes the power grid, oil pipelines, etc., as well as the public digital infrastructure that India has been able to put through the UPI. You might have experienced UPI payments very easily now in India. So those kind of infrastructure, the Aadhaar card, which is the biometric identification, it's a public digital infrastructure. All of that critical infrastructure is under threat. All the internet protocols, they're under threat. Various different email applications, blockchain applications, which rely very heavily on encryption, the digital signature that we are come used to in the digital world for all the document signings and even the legal documents that we do. All of those are encrypted with some or the other type of an algorithm currently. There are two types of algorithms or mechanisms, symmetric and asymmetric. The symmetric algorithms, they are typically used for the data at rest, that is data is stored onto the systems, whereas asymmetric cryptography is being used for data in transit. All of us, we are used to having the data in transit from one point to another point very easily. That is all under threat because of this new advancement that are rapidly advancing onto us. What can the cyber criminals do really? Even if they get hold of some of the data, we do not have a quantum computer right now. And maybe after a few years that you might get hold of a quantum computer, does it really mean that I have to worry about it now? So they can decrypt the sensitive data because they will know how to solve that encryption, decryption itself directly because they have a computing power available to decrypt. They can do a fraudulent authentication. That means you will not even know that a fraud person has entered into your system because they are entering in a legitimate way. They're solving your encryption challenge problem and entering as if you are the real person who is supposed to hold that encryption key. They can forge the digital signatures and they may be able to get your document signings completed. Legal recourse you will not have because it's digitally signed. But more importantly, on the left-hand side that you can see the harvest now, decrypt later. That is the problem that we should worry. We need to worry now. And what does that mean? You will have certain type of data that you may think that even if it is stolen right now by intruding into my system, I'm fine because that data will not be possible to decrypt. And maybe after a few years they decrypt, so what? That might be a thought process, but that is where exactly the problem that we have. So this chart is trying to show you that on the left-hand side there are various sources of data for us to generate the data. On the right-hand side, it is showing different types of data that will remain valid for years to come, such as your passports and biometrics, your vehicle-related data, your aircraft. So in some cases, there is a HIPAA, that is a healthcare-related act, or certain legal areas where you have documents that are valid for 30 plus, 20 plus years, and including your intellectual property, which is going to be with you forever, that you will like to preserve. And even that crown jewels, they may get stolen right now. They're all encrypted, maybe highest encryption level that you currently have available are being utilized. You may feel it is safe, but that data is still valid even after 5 years, 7 years, 10 years, when a hacker, maybe it's non-state actor or state actor, they may get hold of enough quantum computing capability to break that encryption, you will be in trouble. So you will need to take notice of that and you will need to start now. So this danger timeline, when is it going to materialize? So there is no one timeline or given date on which all this will be available. There are many different companies, organizations, countries, including IBM being at the forefront. They are developing a lot of quantum computing capabilities. We believe that by 2030, enough computing power will be available somewhere to start breaking the algorithms, maybe even earlier. at least some of those algorithms which are of a lower level of algorithms currently, maybe 256 key length or TLS 1.0, 1.1, some of those things may be easy to break. Those who have upgraded to the more robust algorithms, it might take more time, but it will break. Everything will be broken after some time because the quantum computing is able to solve that problem of a prime number factorization. And the document that we can see will take a lot more time to migrate all of our systems to go to the next standards of algorithms. By the time that we do, maybe the data is insecure because they can still currently harvest it and they will be able to decrypt all those non-state actors, state actors, which are bad actors for us. So let's talk a little bit more about cryptography itself. What does it mean? So the current traditional public cryptography standards, they use this prime number factorization problem, and that is not quantum safe because the prime number factorization itself will be solved. We need something that cannot be solved by quantum computers as well as the classical computers because both of them, they are going to coexist. For years to come, the classical computer will not be replaced by quantum computer. And if you want to know more about quantum computing, when you visit the booth, I think you can understand a lot more. The quantum computer itself has got only specific use or use cases to solve. The classical computers will be communicating with quantum computer to solve some problems, get back some answers for us to use. The classical computer will also attack. Now, by the way, the quantum computer is not a supercomputer of the today's computer. So it is worst at solving some of the problems that we take easily. For example, that P into Q, finding a product, is very easy for a classical computer, and we have run a lot of tests on it. It will take more time to solve that same simple equation of something, two prime numbers to multiply to find a product will be difficult for quantum computer to solve because it's a different paradigm of computing completely. So what do? We need to have some algorithms which will be difficult to be cracked by classical and quantum both because both of them will be used by the hackers together. So what we need to do is a different type of mathematical problem that we need to throw at these machines that will not be able to solve, something called as lattice-based cryptography. So that lattice-based cryptography is essentially a needle in a haystack problem, n-dimensional array in which this key will be stored that cannot be easily found by classical and quantum computers both. For all of this, this kind of mathematical equations, we need to come up with some kind of standards because anybody else utilizing that encryption, just like the current algorithms, they are based upon standards, they will need to be standardized for the future as well. And with that in mind, the National Institute of Technology and Standards, the NIST is the agency in US as the government agency which sets all the standards to be used for the US government and all other entities operating within US. They have started right from 2016 when the threat was known it will come in the future. They had asked for several government, private, public and academic institutions to submit algorithms, suggest different algorithms that can become a standard in future. More than 80 algorithms were proposed by various parties. It went through robust checks and balances and trying to figure out whether they will be able to get them to break through quantum computer in future. In August this year, they announced the standards. The one algorithms, those can be used as standards for implementation for the post-quantum cryptography era. You can see the names there at the top there, Crystal Kyber, Crystal Dilithium, Falcon, Sphinx. These were the algorithms submitted by IBM. They were all chosen. All others were not chosen because they were broken. So you can see that IBM has been doing at the forefront of all of this innovation, not just creating the quantum computing, but the quantum safe world as well. And our researchers, mathematicians, they have been at the forefront to try and create some algorithms which are becoming standards again, just like what we did in 1974. But there is more, because you do not know what lies in the future ahead for quantum computing or any such other different type of computing mechanisms. In future, we may be able to even break this kind of a lattice-based cryptography. What do we do then? So we'll not be repeating all the whole cycle again, and hence NIST has announced and asked more algorithms to be submitted. Several parties have submitted different algorithms that you can see at the end, draft standards phase. Again, for the next phase of algorithms, we have submitted different algorithms called as multi-quadrant variate equations or isogenic algorithms. So some of those are hard mathematical problems that we believe cannot be solved even with a more advanced quantum computer in future. All of that will go through a scrutiny, but again, NIST has been again doing all this kind of a work to find out whether these algorithms, they will survive the attacks from quantum computing and classical computing together. These standards, they are now getting implemented by several organizations world over. So this is just showing those 4 different algorithms that were submitted by IBM. By the way, the 4th algorithm was actually submitted by someone from a startup company, but who has joined IBM. So IBM has knowledge, but does not make it proprietary. These are all open standards to be followed and implemented by others. That is what has been done, but IBM's contribution has been nothing commercial here. It has been scientific and academic in nature. Now again, these standards, they are being followed world over. This chart is just trying to show that countries and jurisdictions across the world, they follow NIST as a standard to begin with, and they may have some more customizations or additions to those standards to take it into their jurisdiction. But they have already published a lot of guidance, or they are starting to plan as to how do we transition to a new cryptography world. As I mentioned, 2030 is what is being projected currently. And the National Security Agency, they have advised and they have come up with a guidance and executive order by the President of United States saying that by 2030, you will need to be compliant. Your systems will need to have quantum safe cryptography in use. Otherwise, you will not be able to transact business with the government entities at all. And also, the regulated industries will not be able to operate. So I think you can see that the threat is real. And still 2030 looks like a long time, but believe us, we have been through all this journey before. For any kind of standards to move from A to B, it takes a long time to evolve consensus correctly, as well as implement, test it robustly, and then be able to say with confidence that we are quantum safe. So it is going to take years and years for us to complete, and we may not be even done by 2030. You can expect a lot more hacker attempts at critical systems to continue, and hence there is a mandate and a government regulation to try and get all the critical infrastructure safeguarded. Now, I will talk a little bit more about what IBM is doing to help all this transition. Apart from getting the quantum resistant algorithms, as we call, those 4 algorithms, they are currently selected, some more will come. We believe that there is a real problem that we do not even know what is our or what is our cryptography posture and how can we protect against quantum attacks in future. So we have to start with the cryptography usage in your system itself. That is on the rightmost top, discover, that is the phase. So we know that a lot more application code written in Java, Go, C, C++, Python, and several other languages is currently using cryptography elements which are not known to the central the repository where we can actually track the usage and maybe make a plan to change all of that. So that migration itself is going to be difficult since we do not know where it is getting used and what kind of cryptographic algorithms they are currently getting invoked. The bottom part there, observe, that is where we need to look at the dynamic portion. You may have to work with so many other different vendors and third-party systems to be able to complete your transactions. You do not know whether they are quantum safe. How can you ensure that the end-to-end transaction is quantum safe? So we'll need to understand and observe the network traffic to find out where all cryptographic calls are getting invoked. Are they using older standards, newer standards in the current scheme of things? How can we prioritize? So in doing all of this activity for observing or discovering through static code or dynamic network elements, there is some need for another standard to evolve called as cryptography bill of material. Something like a standard software bill of material that is in use at the moment which allows you to have all the software components and their dependencies listed in a particular fashion to understand what software you are using. You will need to have something, what cryptography you are using in the first place. Otherwise, you will not be able to make a plan, what will you remediate. So that cryptography bill of material is also a standard that has been advocated by IBM. We have contributed a lot heavily. That is getting standardized in the industry now with Cyclone DX as an organization which publishes those standards. I think we have a very good standard at the moment created that needs to be adopted by the industry so that all other players in the industry, be it networking to operating system hardware and application developers and application software product developers, they will be able to publish their cryptography bill of material to other consuming parties, and we may have to actually use those cryptography bill of material as a standard for the government regulators and agencies as well to indicate that yes, my software, my hardware is compliant with certain standards or guidelines. The last part is the remediator or transform part, wherein we have several patterns that we have established which will allow you to start remediating. It's an evolving process. Today we are with some kind of algorithm implementations, not all. Also we have certain things called as adaptive proxy, which will allow you to terminate your non-quantum safe connections to your systems correctly and make a quantum safe calls to your backend systems. So it is trying to put a gate in front of all of your the legacy systems, which you will not be able to change that easily right now to make it quantum safe, at least one level of protection. There is something called as performance test harness. So there is an apprehension that all these new mathematical problems will be hard to solve. Will that impact my performance? What is really performance? You are currently able to encrypt and decrypt at a flash of a second, a very small amount of time within a second, and hence you do not even realize that the data is getting encrypted or decrypted. If a hard mathematical problem is given, will it take more time than what we are doing right now? So we'll need to test that as well in your environment, in your systems. We have proven so far with all the research that we have done. In only very few cases, there might be a degradation of performance of like couple of percentage, 2%, 3%. But in some cases, actually, the newer algorithms, they are performing faster than the current algorithms. But you will need something to make sure that your performance is not degraded. That is also part of that remediation capability. So IBM has been developing all these kind of capabilities, and they will continue to evolve over a period of time. They are all available for the other organizations to adopt, use, and they will be able to start their journey on the quantum safe future. I mentioned a bit earlier that maybe a newer algorithms will be required on an ongoing basis. This is called as crypto agility. At the heart of that is automation. That means you will need to be able to have your systems to adopt to newer standards and newer algorithms in an automated fashion, for which you will need to do your architecture in such a way. Now that while you are touching your systems and modifying the systems, you should be able to change your architecture to allow that automated fashion in which you can change your algorithms or calls to the algorithms maybe from a central place. Whenever you see that there is a threat emerging because of the existing algorithm that are getting broken, you should be able to call something different, and you should have a governance on top of that as to how will you govern all this cryptographic estate that you have and be able to make sure that you are not under threat. So this crypto agility is also one of the other standard that we are proposing, in which we will need to get some kind of a guidelines, best practices instead of standards. I would say that will need to be adopted by the industry as a whole, and maybe we can have a more crypto agile environment. So this 5 steps that we have outlined here, the first, second, third step is essentially I talked about identifying, maybe remediating and getting a transition done. The fourth step is that complying with ever-changing standards and regulations. With the advent of quantum computing capability, we know that not only just the algorithms, but even your standards, regulations, they will keep on evolving, changing. As soon as we see a lot of different threat, we will need to change those standards and algorithms and regulations. We do not want to bog down the business by excessive regulations. There may be more simplifications as well that will come up with a different kind of a technological approaches, but that will not be static for decades just like it has been currently. And hence you will need to have some way of that agility to allow you to change the systems more easily to make yourself more confident about your crypto posture, and the skills and knowledge gap. And with the forum like ITU and WTSA, I think some skills and knowledge gap also will need to be bridged by the professionals around the world who will be working in this field of crypto agility. I'll just draw your attention to one more technique that is being in use currently, something called as quantum key distribution. So post-quantum cryptography is my topic, and we are heavily promoting that. Quantum key distribution, IBM was one of the first inventors of this technology as well, and it is being advanced at the moment a bit more. But as you can see at the bottom, that allows you to do a lot more super confidentiality, the quantum key distribution. That requires something more physical hardware for you to generate random numbers and be able to transmit the keys across the network through fiber optic cable. So there is some more hardware dependency as well. But that does not, in the current state, it does not allow you the authentication, integrity, and non-repudiation. There are three more important parameters for the overall enterprise world that will not be allowed in that. But there will be certain use cases where quantum key distribution alone, or maybe in combination with post-quantum cryptography, those algorithms will be useful for us to implement, especially some of the areas where defense and security related applications, the quantum key distribution is more relevant than other telco, banking, financial services, and many other areas where post-quantum cryptography is more relevant. Now coming back to the specific areas of telecommunication, this is the forum for telecommunications. As you can see, there are different areas in the telecommunications itself, which are use cases for us for the quantum safe part of it. You can see the network, the systems and processes, enterprise, government areas. You can see the lawful intercepts and many other mission critical communications, consumer payment services we talked about a bit more, but even the operators, roaming, settlement, many other areas where you have an encrypted data going back and forth or being stored, all your customer consumer data that you are storing on your data center side as part of the telecom operators. I think you will need to take notice that we'll need to work through all these use cases, and several components of all of these transactions, they will need to be secured for quantum future. To advance this quantum computing and quantum safe posture, we have been partnering with Vodafone since last year. We announced the collaboration with Vodafone, and here a little bit case study that I'll talk about Vodafone as well right now. So their goal was to accelerate their understanding and readiness in the first place, because a little is understood about your current cryptography posture and what quantum computer can do in future to break that. So even understanding that, identifying your heat map, where all are your cryptographic vulnerabilities, how can we strategize and plan for that heat map remediation, even compliance requirements to come up with, how can we establish something that can be given back to the community and to the government bodies to adopt as a compliance requirements, how can we optimize the supply chain, because all of the vendor, third-party vendors that are required for us to have this big telecom infrastructure to comply with all the standards is just not going to be easy. Our approach was to try and work with them on the strategic guidance part, as well as creating some new technological innovations. The circle chart that I showed about the discover, observe, transform, all of that part is actually being applied and being evolved together with Vodafone in their environment, in their labs, in their infrastructure. So getting the strategic alignment and the direction for how do they approach this as an overall problem, that was one part. And then the second part was the technology, where we have actually put in our products or the technology explorer, advisor, remediator, these three areas into their network. We have come up with something more, and I'll show it on the next slide as well. We have been able to get the data out of this. So you can see here the cryptographic inventory posture, the technology that we have created, which allows you to get all the details about your network operations. We are not introducing any new agents or nothing intrusive. Existing agents that are collecting the data that is being harnessed, but looked at it from a cryptographic angle, which we are not doing at the moment. So that is what we have been doing. You can see the cryptographic inventory in a bit more listed kind of a manner there. That goes down to your base station and other transponders and various other specific elements in your network that you can actually scan through, understand. The right-hand side there, at the farthest right side, it shows about the posture of the cryptography. The slides there, not all visible with a purpose. We do not want to share all this information very easily outside of Vodafone and IBM collaboration. So that's the reason. But you can see certain things that can be automated, generated. It's not a manual task for you to go and find out where is my cryptography, what is under threat. You can see in more details on the left-hand side once you go into, for example, this is a Nokia base station 6340, in which you can see all sort of stuff and what is really under threat, what is being utilized currently, what will be broken in future rather easily. So you'll have to start prioritizing which actions you will take first, because you need to make all of your entire enterprise and the network safe, but you will need to start somewhere. Where do you start? This is what it's showing that. This kind of a network diagram in our technology stack with Vodafone collaboration that is allowing you to drill down multiple levels of your elements and be able to find out which one you will need to address first, and whether it is really compliant. You will need to continue to scan it further, and you should be able to show the posture that as compliant to the regulatory bodies once you are able to get to that. But that's not all. It's just not about IBM and Vodafone alone trying to do this industry forward. We need to have the entire industry, entire government and regulatory bodies to move forward together. Then only it is possible, because this is everybody's problem, and one company alone cannot solve anything here. So we have been contributing a lot to industry consortia as well as academic councils and many other areas. This is just chart trying to show that. So for example, this Post-Quantum Cryptography Alliance, this other National Security Center of Excellence. More important for us here is telecommunications and GSMA. The GSMA as a body has got now a different task force that is created for Post-Quantum Telco Network Task Force. IBM and Vodafone, they have been the founding members of it, and IBM is currently the chair of this task force, which is contributing a lot more to the overall understanding of what is required for us to make the quantum safe future. In different areas of standards, regulations, compliance, interoperability is very important, because if the different parties involved, they are not adopting the same standards, they will not be able to handshake the encryption, decryption easily, and you will slow down all the system. So we need to make sure that, as well as the backward compatibility, we will not be able to change all of our systems and the hardware gear in one shot. So we'll need to continue to make sure that you will have a heterogeneous environment. That means something will be at a lower standard than the newer standards, and all of that will need to operate together. There are other sectors which are dependent upon the networking infrastructure, as we have seen earlier, and we know all. All of that will need to make sure that it is in fact the backbone of telecom infrastructure, together with the front end of those servers and applications and end user mobile applications or such other interfaces. All of that is seamlessly working. So all of that is also part of this task force as a mandate, and the critical national infrastructure to safeguard as a special focus on that. So what we have been doing, I'll just summarize a bit here on this slide. What we're trying to say that, this task force, I explained what all different areas that the task force is mandated to do, but also we are coming up with specifically supporting, planning, sharing the best practices or the analysis that we have done through different kind of a paper that we are publishing together. There are certain platforms and POCs that we are doing, the trial that we are doing for various technology stack that we mentioned about. So all of those also will be shared as part of this task force for other members to come up with a more common consensus approach that they can take. We have been publishing some of the material through the World Mobile Congress, and here as well now with the IMC and otherwise. We will be publishing more and more material from our experience working together as IBM and Vodafone collaboration on the specific post-quantum area and the GSMA standards that will evolve with this task force. So already on this task force and the GSMA itself, there are 60 plus members. I will invite more and more team members to join. IBM is a co-chair, so if you really need any more specific information, you can contact me and I will be able to help you connect with very key stakeholders who will listen to your point of views and be able to get that all together for the industry to move forward. There are certain business value report that IBM has been generating, and there is a lot more different material, but I just wanted to highlight a couple of areas where we are publishing a lot of our research on quantum computing as well as quantum safe. You are free and invited to go through and read and stay tuned to all this new material that is getting published, as well as the quantum roadmap that we publish on our website that will give more and more indication as to where we are in terms of qubits and calculations, what all real world problems that we can solve, as well as you can get an idea as to when this cryptography problem may get hacked. So that's all I wanted to share. Any questions, any comments? Sure, thank you. We need to give them a...
So like when we design protocols for like healthcare sensor networks or VNet, we actually consider security parameters as well as computation cost, as you discussed with us. And the one more thing which we also consider is communication cost. So do lattice provide less communication cost, or how does it outperforms the like existing cryptography protocols like hyperelliptic curve or elliptic curve? So that's what I am asking. Basically, communication cost में कैसे perform करता है ये lattice based crypto?
All right, so this is what the performance test harness that I talked about, and maybe you can experiment the algorithm that you are trying to use in your area. Communication cost should not increase. Computation cost may be a hit only if in certain cases the algorithm that you are using, the existing algorithm you are using and the newer algorithm, elliptical curve or any other such areas, that you will need to actually test and experiment because the kind of the server CPU computing power that you are using, that also matters on the other side as well, because this is a public key infrastructure, so there will be a handshake on the other side. Maybe the other side is not prepared for addressing, but so far all of the existing algorithms that we have seen versus the new algorithm being proposed, that test indicates that we do not have performance degradation, because that has been one of the main factors for NIST to establish standards. If a new algorithm is very difficult to solve but is performing poorly, why will they publish as a standard? So believe me that this will be taken care. However, still you will need to test in your own environment rather than somebody else needs their labs, and for that also we have created a utility which can be utilized for all of these things. Now there will be different more algorithms that will come up. Maybe there will be challenge for those algorithms, but as we move forward we will test them.
Okay. And one more question I have, like Kyber, dilithium, these all algorithms are based on lattice-based crypto or some other mathematical assumption?
No, lattice-based cryptography.
Lattice-based cryptography.
Yeah.
Thank you.
Sure. Yeah, there is a question here as well.
I have a generic question, as I'm not aware of the quantum world. My basic question is, what is difference between post-quantum, quantum communication, like how quantum communication is different from this?
Okay. So quantum, and as part of the quantum mission in India, there are different four work streams or work groups created. One of this is quantum communication. How will it aid your communication revolution? The telecom sector itself will undergo a bit more change, because you will be able to do a lot more different problem solvings for the using the quantum computer. So that is what is called as quantum communications. That there is a positive side of the quantum computing. Whereas when we are talking about post-quantum, it is the word post-quantum is being utilized because before quantum and after quantum, something like Y2K, you had a crisis before Y2K and after Y2K is a totally different set that you have to change. So the word post-quantum is coming only because of that. Whenever, it may not be a definite time period, but whenever enough quantum computing capability is available, what will change negatively? And one of the main thing that will change negatively is the current cryptography that you are using. Because the cryptography is not an impossible problem to solve, but it is near impossible with the current capability. That's what was done. And whenever you have a newer algorithm, that also may be broken. Maybe we'll have something.
So basically, post-quantum is about dealing with the security vulnerabilities of the quantum world. So
not the quantum. I mean, when you have quantum computer available, your existing vulnerabilities will be exploited.
If we are living in a world which is completely dependent on the quantum technologies, at that time current cryptography and techniques would fail, and for that we need this post-quantum techniques.
Yes.
Right.
Yes. Correct. Correct. Okay. Right. All right. We may not have time for more questions. Are there any questions? Okay. We are good. Thank you. Thank you so much for your attention.